Please take a moment to pause the video and reread the problem before listening on. In parts A, B, C, and D, we are asked to find the position of the object at 4 different times. But we are also told that the position of the object moving along the x-axis is given by this position equation. X would be the position along the x-axis, and then t would be time. So for parts A through D, all we need to do is plug in the various times, and that's going to allow us to calculate the position of the object at those times. So we'll go ahead and set up those calculations. So we have gone ahead and plugged in all the times. Now we just need to plug that into our calculator and simplify. When you do that, you should get 0 meters, then -2 meters, then 0 meters once again, and then 12 meters. So those would be the 4 positions at those 4 times, and the correct answers to parts A through D. In part E, we are asked to find the object's displacement between t equals 0 and t equals 4 seconds. So let's think about what the definition of displacement would be. Displacement is often represented by a change in x, which just means your change in position. So we would have to take the position at 4 seconds, which is represented as x of 4, and then subtract the position at 0 seconds. Now, fortunately, we have already computed those positions. We know that the position at 4 seconds is 12 meters, and the position at well, actually, we haven't calculated the position at 0 seconds, so we're going to actually need to do that first. My apologies for that, but I didn't realize we didn't do that. So that's okay. To get the position at 0 seconds, we would plug 0 into the position equation, just like we did for parts A through D. So let's go ahead and do that. And there we have done it, and we can see actually that the position at 0 seconds is known to be 0 meters as well. So we have the position at 0 meters, at 0 seconds, and also at 4 seconds. It's been a rough morning. So let's go ahead and plug in. X of 4 was 12 meters. X of 0, we just figured out, was 0 meters. We make that subtraction. We can see that the change in position, aka the displacement, is 12 meters. So that's the correct answer to part E. Looking at part F, we are asked for the average velocity for the time interval from t equals 2 to t equals 4 seconds. So t equals 2 to t equals 4 seconds. Let's think about what the definition of average velocity would be. Well, of course, we've been learning in this chapter that the average velocity, which we can label as v with a bar, that is going to be the displacement divided by the time interval. So in this case, the time interval, again, in pink there was from 2 seconds to 4 seconds. So we always take the final time and subtract the initial time. So 4 seconds minus 2 seconds. And then the delta x would be the position at 4 seconds minus the position at 2 seconds. We have those positions. We go back to our data here. The position at 4 seconds is 12 meters. The position at 2 seconds is -2 meters. So we'll plug those in very carefully. We do need to be careful because it's going to be 12 meters and then subtracting a -2 meters. So watch that subtraction of a negative. In the denominator, we just have 2 seconds. So 12 minus -2 is 14. Divided by 2 is 7. We're left with 7 meters per second. That is the average velocity in that time interval, the correct answer to part F. We look at part G, and it says to graph x versus t from 0 to 4 seconds. So we'll go ahead and do that. There is the graph. Again, we're only graphing it at the interval from t equals 0 to t equals 4. And basically, we just plug that into a graphing utility, and we got this curve right here. That would be it for part G. We've plotted the x on the y-axis, which is the position, against the time on the horizontal axis. But now there was a final part. It says, indicate how the answer for part F can be found on the graph. Well, recall in part F that we were looking for the average velocity from 2 to 4 seconds. So if we look at the position at 2 seconds, let's label these very carefully. So here's the position right there, that black dot at 2 seconds. Here's the position at 4 seconds, that other black dot. And the question is, what feature of the graph would give us the average velocity? And we can see that the slope of the line segment that joins those 2 points would give us the average velocity. So graphically speaking, if you ever needed to find the average velocity between 2 points, you would just draw a line between those 2 points and determine the slope. Now, maybe as an exercise, we can determine the slope to sort of prove that we get the same average velocity. Remember that slope is a change in the y-coordinate divided by the change in the x-coordinate. And so we can see that the change in the y-coordinate would be from 12 to -2. So there again is that 12 subtract -2. That would be the change in the y-coordinate. And then the change for the x-coordinate would be the 4 seconds subtracting the 2 seconds. And of course, when we work this out, we're still going to get 7. So again, the slope of that line segment would also give you that average velocity between those 2 points on the graph.